So we're now moving into a new chapter. We're going to talk about the derivatives of measure, and our main goal is to prove the Radon-Nikodym derivative, which we'll cover in the next lecture. So before we do that, we need to prepare ourselves a little bit. So let's talk about this notion called the signed measure. Okay, so it's a generalization of the measure that we saw already. So let's keep the definition first. So suppose I have a measurable space. A signed measure is essentially just removing the requirement that my measure need to be finite, need to be positive. So I can now take a value, so map the sigma algebra A to negative infinity to positive infinity. So here I want it to be preserve all the nice property of a measure. So in particular, I want the measure of the empty set is still empty. And also I want, if I have some disjoint union, then the measure, the signed measure of their disjoint union is the sum of their measure. Okay, so here because I'm allowing mu of these e can take negative value, so the sum I have to make sure the sum is converging in the absolute sense. Okay, so the convergence, every convergence is in the absolute convergence, and I also need to make sure that because now I can have positive or negative infinity, and adding a positive or negative infinity is really tricky. So I just want to exclude that. So the last property here, so color this one. So this one is just essentially saying mu can either just take a positive infinity but never negative, or the mu can just take negative, never positive. Okay, so it can only take at most one of the positive or negative infinity. So in this case, the mu, we will never run into a situation where we're adding a positive infinity to a negative infinity. All right, so that's the basic definition. So just a little bit motivation why we care about the sign measure is the following. So recall we saw measures have some linear structure. So suppose I have two measures, mu1 and mu2 there. Just some measure, just regular measures on this X and A. Okay, we saw they have linear combinations. Well, we can only take the positive scalar of them, and I can build a new measure. Okay, so sign measure allows you to take their negative. Okay, so if you take mu is equal to mu1 minus mu2, here I need to assume that at least one of mu1 and mu2 is not infinite. Okay, so at least one of mu1, mu2, or let's just say one of them is finite measure. Okay, so I take their difference, and their difference is a signed measure. Okay, so this one is a signed measure. Okay, so in other words, I'm basically, this is a natural object to look at if I want to talk about linear combinations of finite measures. Okay, so I can now multiply negatives of a finite measure and I sum them up. I get something called a sign measure. Okay, so there's also another thing that's kind of quite natural. We're going to see like a lot of sign measure come from this way. So if I take a mu f is measurable on some L1 of nu, okay, so some L1 function, and let's just assume the f plus the mu or the negative part is not infinite. Okay, so one of them is not infinite. Okay, so then I can define a new measure. So I can call mu of e to be the integral of the f of x, the mu of e. Okay, do the integration, but over the set e. Okay, so on your assignment, you already saw that if f is a positive or non-negative measurable function, then the integral you define this way end up with a measure. Okay. But in general, if you have an L1 function, you can do the same thing. This mu function is very similar to a measure, but we allow us, the mu is allowed to take negative value, so this is a signed measure. Okay, so here's two examples of why we care about the signed measure. And so a lot of nice properties hold for a sign measure. So for example, one of them is the continuity along increasing and decreasing chain. So suppose I have some E1 containing E2 and so on, okay, and mu is some sign measure, then the union of these En is equals to the limit of mu of En, okay? And if I have a decreasing chain, okay, so now everything is decreasing, then I have mu of their intersection. This one is also equals to the limit of mu of this En. Well, of course, the second one is given the mu of E1 is not going to be the positive infinity, okay? So the proof is really the same as what we did in regular measures. So it's basically the same proof. So I'm going now proving this. This is an easy exercise. Okay, so exercise. Okay, you're essentially just using the sigma additivity of a signed measure, and nothing really changed. We need to be a little bit careful right now when we talk about signed measure about the null sets. Okay, so here I want to make a few definitions. So let me try to make the definition first, and I'll explain what I mean by null sets. It's a little bit tricky. Suppose I have a signed measure, and let's consider a set A, E inside the sigma algebra. Okay, so I call this E is a positive set. If the following happens, if for every subset of this E, I have mu of this subset is going to be non-negative. Okay, of course, F is inside the sigma algebra. And I similarly define what do I mean by a set to be negative is just means for every subset of this E, okay, it can be equal. The mu of F is going to be less than or equal to 0. Of course, F is inside A again. And finally, I call a set to be a null set, okay? So usually for a measure, the null set is just, the measure is going to be 0. But now let's say a null set, it means for every F subset of this E, the mu of F is actually equal to 0, okay? So here F is always coming subset from the sigma algebra, okay? So why we make this definition of a null set and also similarly the negative and positive? Well, let's take an example. So if I just consider a set with 3 elements, 0, 1, and 2, and I consider a measure, let's say, call it mu to be the Dirac measure, delta 0 minus Dirac measure of delta 1, okay? So as you may notice, I have a set F, okay? So if I take F just to be the 0, 1 set, then the mu of this F, well, is basically equal to, well, the delta 0, 0 is in F, so it will give me a 1. But delta 1, well, 1 is also in F, it will give me a negative 1, so it's going to be 0. So F is a measured 0 set, but F contains something that's positive and something that's negative that just happens to cancel out. So F itself is not very measured, like the measure of F, even though it's 0, but its subset is non-zero, so we don't call this F null set, okay? So here F is null, okay? It's not null set. Okay, you can convince yourself based on this example why we define a null set in this way, okay? And let's just work on this example. So if I take a E to be 0 and 2, you can convince yourself that this is positive, okay? So because it basically avoids the negative mass at point 1. And if you take something like running out of letter, maybe let's call it N to be 1 and 2, and that's going to be a negative set. Okay, so it avoids the positive measure at 0, basically. All right, so now I'm going to prove some nice property of these positive and negative sets. So let's do a little lemma. So suppose I have a En as a sequence of positive sets, then what I can show is that their union is also positive, okay? So this is what I claim. And of course, you can replace this positive by negative or even by null sets, okay? So they're really the same proof. I'm only proving the positive part. You can write out the negative or the null sets part. All right, so let's prove this fact. So basically, I want to show that this union is positive. So First of all, whenever we have a union of a countable union of sets, so here everything is countable, I can rewrite this countable union as a countable disjoint union. So here I can write it as union of some Fn, where here Fn are disjoint, and each of these Fn is a subset of En. Okay, like we already seen many times how to construct this Fn, so I'm not going to talk about that. All right, so now let's take for every F, I want to show the union of En is positive set, so I need to show every subset of this En is having a non-negative measure. Okay, so here I take F is inside the union of En. Of course, I assume F is inside the sigma algebra. Well, then what I can do is that I can write F as a countable union of some F intersect these Fn. Okay, now it's a disjoint union. Okay, each of them is inside A as well, and each of these F intersect Fn, that's going to be a subset of Fn first of all, and Fn is a subset of En. So the measure of a subset of a positive set is going to be non-negative, so this is non-negative. And F is a disjoint union of a bunch of these sets, so the mu of F is going to be the summation of these mu of F intersect Fn, which is going to be non-negative. Okay, so we proved basically this just shows the union is a positive set. All right, so now we want to prepare ourselves for the first big theorem called the high-end decomposition theorem. And to prepare us, I want to prove a really technical lemma here. So let's do the following lemma. I want to show the following. So suppose, let's say mu is some signed measure. Okay, so this is some signed measure. And let's make assumption, well, because it never take, it only take one of the positive or negative infinity, let's just assume it's never positive infinity, all right? Now let's suppose I have some set E which has a strictly positive measure, okay? And the claim is that there exists E itself may not be a positive set because it may contain some negative measured subsets, but it actually contains a positive set. Okay, so there exists a P containing E where P is positive. Okay, this is my claim. All right, so the proof is rather technical, so let's try to go over this. So first of all, if E is positive itself, then there's nothing to prove. Okay, so this is done. Okay. So otherwise, then I know that there exists some subsets, let's say A containing E, where the mu of A is negative, okay? I mean, not less than infinity, but less than 0, all right? So now I can pick something that's as negative as possible. So let's let M1 to be the smallest integer such that I can find a set A1 containing E so that the mu of this A1 is less than 1 over M1, negative 1 over M1, okay? So I'm picking an A1 that's a negative subset of E, which is as negative as it can be, okay? So M1 is the smallest integer, all right? So now after I've done that, let's just remove this negative subset, the measured negative subset. So let's let E1 to be E take away this A1. Okay, so this is a subset of E. And if, again, I have two cases, so if E1 is positive, then I'm done. Otherwise, then E1 is not positive, then there exists A2, which is negative inside E, okay? The measure of A2 is negative, okay? So I can take an A2 that's as negative as possible as well, okay? So I should say otherwise, let's let M2 to be the smallest integer such that there exists an A2 inside this E1. Okay, so that the mu of this A2 is as negative as it can be. Okay, so minus 1 over M2. Okay, so I can just repeat this process. Okay, so either I get some En which is positive set. Okay, En is positive, or if not, then I can just continue and I get some these An. Okay, so each of these An is contained inside E of n minus 1, in fact. Okay, that's just by our choice. And the mu of these An is going to be less than or equals to 1 over Mn, where Mn is the smallest integer, so that that's the smallest mu of An I can find inside E of n minus 1. Okay, so I now have the sequence. All right, so now let's let the following. So let's let E to be, well, now I have this En each time I'm taking off these An part. So let's let P to be the intersection of all of these En, okay? So here recall the En is essentially just En minus 1 take away the An, okay? So it's a decreasing chain of sets, and I take their intersection. This set is certainly measurable. Okay, so now my claim is that this P is the positive set that I'm looking for. Okay, so let's claim P is positive. All right, so first of all, this E, you can write it as the disjoint union of all of these An. Okay, so each of these An coming from En, and because the way we define this En, these An are disjoint, and if you take away all the An, you get the P, so E is a disjoint union of these. Okay, so by the sigma additivity, the mu of this E is going to be the mu of this P plus the summation of mu of An. Okay, but each of mu of An is less than or equals to less than some 1 over Mn, so this is less than mu of P plus some summation of 1 over Mn. Okay, and by our choice, the mu never takes the positive infinity, so this is not equals to positive infinity, and the mu of P is not equals to positive infinity. So I have some finite number, and the left-hand side is less than some finite number minus a series here. So it just means the series has to converge. Okay, so the only way this can happen is that the series converge. And you know, when a series like this converge, these integer Mn is going to go to infinity. Okay, that's as n goes to infinity. All right. So now, because of these Mn is going to infinity, it just means as I move along this En, if I want to take some negative measured subset, then this negative measure is just going to get closer and closer to 0. Okay, so that's essentially what it's telling us from this Mn goes to infinity. All right, so now let's suppose I have some f contained inside this P, okay, and I know it's contained inside this En, okay. So if I consider the mu of f, okay, so the mu of f, well, if we think about it, the mu of f by our choice of these Mn, okay, remember what happens is that inside this En, I picked some mu of An plus 1, where the An plus 1 is less than minus 1 over Mn, okay? So it's somewhere between 1 over Mn and 1 over Mn minus 1, okay? Let's assume Mn is not 1. All right, so in other words, there's no mu of some negative value inside this area, okay? There's nothing in here, okay? There's nothing in here. So in other words, the mu of f, because f is a subset of En, it has to be greater than equals to this range. Okay, the mu of f can only live in there. Okay, so this is at least negative 1 over Mn minus 1. Okay, well, now but we have Mn is going to infinity, so this 1 over Mn minus 1 is, well, getting close to 0. That just shows this the mu of f is non-negative, okay? So it's greater than or equal to 0. In other words, all subset of P is going to be non-negative, so P is positive by definition.